So if we pick up the beanbag and go from here to here. Okay, we're going to have to start over. Okay, so energy is the ability to produce change or to do something. Then we have these 4 scenarios in the notes. In part A, the beanbag, it's lifted. At this point, does the system have energy?
Yes.
Because of gravity?
Potential
maybe?
energy.
So potential energy, we don't know what that means yet, but we've heard that word. Something about gravity. So could it do something? Could the beanbag do something?
Yes.
Yeah, what could
It
it do?
It could fall.
It could fall, right? If I had something down here, like, well, suppose this was a brick, right? If this was a brick and I had my hand down here and it fell, right? It could do damage to my hand. This is not going to do much damage, but it could still do something. So at B, let's draw a little circle. So here's the beanbag at A. Here's C. Here's B. So at B, let's draw a circle to represent that the system has energy. And the size of the circle represents how much energy it has. Okay? So just draw a circle at B that represents that it has energy. Make it, the size at least of a nickel. Because we're going to want to write stuff inside. Is your circle really small? Okay. Now we have the toy truck. Evan, can you send the truck down here, or the car? So we've got a little vehicle. And this scenario here is, at A, it's at rest. And then I'm going to push it over some distance. So I'm going to let go when it's about here. And then it's going to slide and slow down due to friction. So I'm going to give it a push. Okay. And B is the moment after I let go. So it's moving at that point. Would you say that it has energy?
Yeah.
Yeah, it's moving, so it has energy. I'm realizing I'm going to run out of places to draw all 4 scenarios. So I'm going to put this one down here. So here's my truck. This is A. Here's B at the instant that I stop touching it, and draw a circle to show that it has energy. That's the energy that it has at B.
Should this be around the same size as the energy at
Between scenarios it doesn't matter, but I would make it the same size. Can I get rid of the glare? Can you guys see okay
Yeah.
without that? Okay, then our third scenario, we have this guy who's, okay, so we've got this little bow and arrow guy here, and A is when the arrow is just sitting here, but it's not pulled back. Then we're going to push it in. So B is when it's at the same height, but it's pushed back. C is just after it's released, but it hasn't fallen yet. And D is when it is flying in the air, so it's partly down. So would you say at B, does the system have energy?
The system's bow? Yeah.
Right?
Well, the system is the bow and the arrow.
The bow and the arrow and the floor and the earth.
At B,
At B,
it can have movement at B,
it has energy.
but C is like when it's actually moving.
Right, it's actually moving at C. So here's interesting because we have energy, but it's not moving. Sort of like the beanbag, right? The beanbag had energy, but the system had energy, but it wasn't moving. So here we have the sense that there's something here that could do something. We have the sense that that has energy. Okay, so let's draw a circle for the little bow and arrow guy to represent that it has energy. So here's my person at A. The bow is not pulled back. Here's my person at B. I tried to show that the bow is pulled back. And then C is just right when it comes out. And then D is when it's falling. So A, B, C, and D. So at B, let's draw a circle to show that it has some energy. Okay, and our last one, D, cup of water. So I took a mug of water, here's what it was room temperature, and heated it in the microwave. So it's kind of hot. Is this picture B? you have to realize with some of these diagrams, these are processes. The mug of water, over time, it's not going to be moving to the right. So the picture shows it, right, at different snapshots, but the mug is not actually moving. So sometimes it's a picture where something is moving. Other times you're just seeing different times separated in space so that we can draw diagrams. So picture A was before I heated it up in the microwave. This is picture B. And picture C will be after 3 hours go by, 3 hours from now. Okay. So right now, would you say it has energy?
Yes.
Yeah, doesn't it?
Yeah. What kind? Why does it have energy?
It has heat.
Does what?
It has heat.
Has heat?
Mhm.
Yeah. And heat is energy.
You have the sense, right, that something more is in there than was in there before. So at B, let me draw the 3 little mugs here. At B, this will represent the energy in the system at B. Now these different scenarios have different ways of storing energy in the system. So what we're going to look at now is those different ways. So why does this have energy? Why does the system here have energy as compared to like this one? What's different about these? What did we do to this? And what did we do to this to put energy into the system?
You
Applied
put a
certain
force on
forces.
I
Yeah,
put a
just
force on it.
any force.
But isn't this like what other things on the table are kind of like this? Can you pass me that little? Which of these two is this guy on the spring more like?
Bow.
Is he
Bow.
more like the bow and arrow?
Yeah.
Or like this?
Oh,
Boner.
He's more like this, right? In this situation, something got squeezed that wants to expand, right? That's not the same as this. Here, 2 objects got separated that want to go back together. And then this one is different. What actually changed about the water, if you get down to a molecular level, what actually changed when you heat something up?
the moving of the
Changed,
molecules.
phase change.
Yeah, the molecules start moving faster. If I kept going, I would get some to evaporate. Then
Yeah,
I would
some
have
phase change probably.
some probably did. Yeah, so the molecules are moving faster. So here we have more motion of molecules inside the object. And then what was the other one? The car. So what happened here, that one had energy because it was moving. We know that something moving must have some energy. So look at the chart there. There are 4 different ways we can store energy in a system. And I'm not going to write, I'll just write it down over here.
So if an object is moving with no forces acting on it at a constant velocity.
Say that again?
So if an object's moving at a constant velocity with no forces acting on
Like
it,
in space.
does it still have energy?
Yes.
Okay.
Uh-huh. Because if you had something like in space,
Oh.
right, no forces, it's moving at constant velocity, if it collided with something, it could do some damage. So
Okay.
that's your
That
clue.
sounds
Yeah, if it could do damage or create a change somehow, then we would say that.
You guys have to
Okay,
get the big one.
so let's write down our types of energy. So the first one, Mark, will you read the first one for us?
Sure.
2 masses are separated. 2 masses are separated. It is only significant when at least one of the masses is humongous.
Okay, that storage mode, what would we call that storage mode? That's this one. When 2 masses are separated.
Gravity.
Yeah, that is related to the force of gravity, and it's called gravitational potential energy. So write this in the chart for the first one. And we have a symbol for that. The symbol for that is capital E, which represents
Energy?
excellent. E represents energy.
Oh, I thought you meant
Oh.
excellent. Like, it represents.
It represents energy, and the little g represents gravitational potential.
Big.
Okay, the next one, my next mark. This occurs when?
An object is moving and has a velocity.
Okay, what do you think the name of that one is?
No,
I already
that's a
said
guy's
it at
meaning.
some
But,
point.
yeah, I
I
forgot
heard
it.
somebody say it. It's one of those energy words you guys know.
Kinetic.
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 Yeah, that's kinetic. Kinetic energy.
Is that like E with a subscript K?
Perfect.
Nice guess.
Mm.
So on top of it today. So that is an E with a subscript K. Okay, Evan, the next one.
Something is stretched or compressed, and it would go back to its relaxed position if it was allowed to.
What
That's,
should we call that one?
I don't know what the name of that is.
What kinds of things do that?
The bow?
Spring.
Springs. What else? Elastic.
These.
Rubber bands.
Something with tension.
So this one is called elastic potential energy because being elastic is that property to be stretched and to go back, or to be compressed and to go back. So this is elastic potential energy. Capital E.
Subscript P.
Yeah, subscript E, but we're also going to put an L there. EL, lowercase EL. And that is
Elastic.
because when we get into electricity and magnetism, we're going to have electric fields and things. So we're going to use EL here so we don't have two symbols meaning the same thing. And Henry, the last one.
Molecules inside AR objects are moving.
Yes. Any idea what that would be called? That kind of
Molecules
energy.
inside.
Molecular energy.
Heat energy.
Yeah, that's a good
Molecular?
guess. Molecular energy.
Thermal
it has,
energy?
You know, thermal energy. It's often called thermal energy. We are going to call it something a little bit different, but you'll see thermal also, so they mean the same thing. We're going to call it internal energy, meaning that it is internal to the object, not meaning internal to the system, right? All the energy we're going to talk about is part of the system, but internal to the object. Realizing I'm a big shadow. It feels very different to be recording this. Okay, so the abbreviation for internal energy is EINT. And these are called storage modes. They're different ways that energy can be stored in a system. So let's go back now to our 4 scenarios and identify how is the energy stored for, moment B in all of these different situations. So what do you think here?
Gravitational potential?
Okay, gravitational potential, and you can kind of do a checklist. You can ask yourself, are 2 masses separated? Yes, this is separated from the Earth. It could fall. Is it moving?
No.
No, so no kinetic. Is something stretched or compressed that wants to go back to a relaxed position?
No.
No. Have I done anything to make the molecules inside the air or the object move faster?
Well, not really.
No.
Now here's an interesting one. Are the molecules moving in there?
Yes.
Probably.
They are, right? It's not an absolute zero. So as long as it's above absolute zero, the molecules are moving. So it has internal energy. But rather than always account for these internal energy things start with, we're just going to say that's our 0 level of internal energy. So you don't need to ever consider the internal energy things start with. We'll just look at how they change over the process. Okay, so none of those other types. So all we have is gravitational potential. So the entire pie, this is a pie chart. The entire pie here is EG. It's all stored as gravitational potential at that moment in time. Okay, the car. And on the diagram for the car, do you see that the surface under the car changes at B?
Yeah.
So to
Yeah.
simplify
I thought that was
things, I'm going to say
not
there's no
supposed to.
friction while I'm pushing it. The friction starts after I let go. So at B, do we have gravitational potential energy?
No.
No, because it's not raised up. Okay. The same thing is true with gravitational potential energy, though, as with internal energy. In a problem, you could just decide, if you're doing your entire situation on the table, you could just say, okay, that's my ground level, and I'm going to consider that to be my 0 level of height. Or the computer went off.